Can I start for this session? Please raise your hand if you want to go with this session. Yes. So let's discuss about the algorithm, that is the simple form, piso-form, and pimple form. So let's discuss about the simple algorithm. Then we are going to compare between the simple and piso and pimple algorithm. Okay. So how I'm going to present this session? First, I'm going to explain you about the simple algorithm, taking the matrix example. Then we are going to see the derivation of this simple scheme, and then after that we will go to the coding part, where I'm going to show the step-wise step how the coding has can be done into the OpenFOAM, and then we are going to compile that code also, and then after that I'm going to compare with the piso and pimple. So this is the complete course plan that I'm going to cover in this session. Okay. So this is the idea. So first I will start with the overview, then derivation, then I will discuss about the pressure and velocity coupling, and then we are going to cover the coding part using the OpenFOAM 9 version that is currently installed in this system. And then I am going to compare between the piso and simple algorithm, and then we will have a final question and answer session. Now speak about the Navier-Stokes equation, means fluid mechanics. So we generally solve these two equations, that is the mass conservation and that is the momentum conservation equation. And if we see that moment mass conservation is simply a conservation law that is everywhere available. So if we study any of the physics, this conservation law is always followed. Here we are following the mass conservation. Sometimes we follow the conservation of the energy and conservation of the momentum also. So here the conservation of mass law derives this continuity equation. So that is the del rho upon del t plus delta dot rho v equal to the 0. That is the continuity equation. And the conservation of momentum comes from the Newton's second law, that is the force equal to the mass into the acceleration. When we apply this conservation of momentum or Newton's second law, then we come up with this equation for a control volume of a fluid. So this is if you apply this Newton's second law to a control volume of a fluid, we are come up with this equation that is known as the conservation of the momentum. So first term is the transient term, that is the del rho v upon del t. Second term is the inertial force. Third term is related to the pressure drop. This term is the related to the viscous force, and last term is related to the external force. Now, this problem is so much important to find the solution that you can, if you search into the Google top hardest six problem in the mathematics. So this is the one among those problems. So this problem is means recognized by the Clay Mathematics Institute, and they have proposed one US million dollar if you find a analytical solution for this. Okay, we are finding the numerical solution that is not going to give you $1 million dollar to US dollar. But if you are able to find a analytical solution for this problem, then you are going to win this amount of price, and you can search in the Wikipedia. You can going to find this problem. Okay, so from there that you can understand the hard how hard how hard to solve this Navier-Stokes equation, and from where this problems comes from, where this problems comes that we cannot find an analytical solution of this problem because there exists a non-linearity, and second one is that there is no a explicit equation for the pressure. Okay, so if you write this equation, this is going to continuity equation going to give you a single equation. But if you write a second equation, that is the momentum equation, in terms of the different component of the velocity, so then we are going to have a three equations.
चलिए
Some- Sorry, someone is asking any question. Okay, so second, so first equation, that quantity equation is going to give you one single equation, but we see the second equation, that is the momentum equation, and if we write the equation into the different component of the velocity, that is the u, v, and w, then it is going to generate the three different equations. So we have a four equation and four variable, that is the velocity, three components, and the pressure. So four equation, four variable, we should be able to get a easily solution. But the problem is that we don't have any separate or explicit equation for the pressure. That is where this problem occurs, that we cannot find the accurate or analytical solution. So the problem of the non-linearity we can solve by using the some iterative method. Okay, this problem of the non-linearity, that is happens due to the this term and this term, that is the convection term, that we can solve using the iterative method. But the problems of the there is no explicit equation for the pressure, still the problems occurs, and that is where this concept of the pressure coupling comes into the picture. Okay, so by using this two method, that is the iterative method and the pressure coupling method, we are going to solve this two equation using the numerical method, and we are going to approximate the some solution. We are not going to get the accurate solution, but we can approximate some value, and that can be useful for my research, for my purpose. So that is why we use the CFD. Okay. Now let's understand by taking this two problem as a matrix form. Okay. So we can write this two equation into the matrix form. So if you see here, V means three components of the velocity, P means pressure. Okay. So if we see these two equation, the first equation and second equation, we can write into the matrix form, that is A into U equal to the FP by FP and 0. So if you see, so if you see this momentum equation, then if you multiply F and this B transpose into the V and P, then this is going to give you this first term going to give you the this momentum equation. Okay, and this term, that is the B into the V and P into the 0 equal to the 0, that is going to give you the continuity equation. Okay, so this is just for the simplification where you can understand the problem into the matrix form. So if you see this second term, so if you are going to multiply B into V, so some component of the V is there, and if we compare here, this side, right side is equal to the 0, so right side equal to the 0, and similarly this first, if we multiply F into the V and BT into the P, we are going to get the momentum equation. Okay, so this matrix is sometimes known as the saddle point. Now this is the matrix. This A is the matrix. We can decompose this A matrix into the lower diagonal matrix and upper diagonal matrix. Okay, so if we, this is known as the Scumber complement matrix, where we can write this A into the form of this matrix and this matrix, and if we multiply these two matrices, it is going to give us this kind of the matrix. Okay, so this is known as the lower triangular matrix, and this is known as the upper triangular matrix. So we can write this A matrix into the lower triangular matrix and into the upper triangular matrix. Now, so this AU become like, this is the completely A, this upper lower triangular matrix and upper triangular matrix becomes completely A. That is the V and P is the unknown, and this is the body forces. Okay. Now the idea is that we can write these two terms, that is the upper triangular matrix and V into P as the V star and the P star. Okay, so this is the some intermediate term that we are assuming here by writing the upper triangular matrix and to this unknown. Okay, so we are taking this is as a V star and the P star. Okay, now for simplicity, in simple form, what is done here? For simplicity, this F inverse the diagonal matrix. There is no any advantage of taking this as a diagonal matrix, but just for the simplicity, we take in simple form as a diagonal matrix. So we can write here F inverse as a D inverse because we are assuming here only as a diagonal matrix. Okay. Now, if you are able to catch up till here, now we can arrive to the algorithm, how algorithm simple form algorithm works. We can arrive from this two major simplification to the A matrix, and here we have taken this is as V star and P star. So remember these two things. Now we can see the how this simple form algorithm works. Okay, so what is the basic idea? First, we start solving this F0 into the V star into the P star equal to the FV. So this we start solving this momentum equation, and this V star is known as the means the momentum predictor step. Here we are predicting the velocity using this momentum equation. Okay, this V star is following the momentum equation but does not following the continuity equation. Okay, if we solve this FV star equal to the FV, that is the body force. So this V star is the following the momentum equation but does not following the continuity equation. Okay, and that is where we need to come up with the momentum characteristic. Okay, now from the second step we we have found the V star. Now using this V star we are finding the P star. Okay, now with this P star and V star we go to the top one step where we are correcting the velocity. Okay, you following the continuity equation. Okay, so if we solve this two equation, this identity matrix, so we are having V equal to the V star minus D inverse into the BT into the P star. So using this P star and V star, we are correcting the velocity, and also we are this P star is already the corrected pressure. So that is why that is how this 1 2 3 4 step will be followed throughout the simulation until and unless our accuracy is reached. Okay. So what is accuracy here? When the difference between the two consecutive velocity or two consecutive pressure is less than the tolerance value which is provided by the user, till then this iteration will follow on. Okay, so this is just a simplified matrix version to understand the problem. Now let's see the derivation part. Okay, so why this pressure velocity coupling is important? Because the choice of stress discretization for incompressible flow is in the centered and upwind methods for the convection term. So in open form, mostly the all variables you see in the open form, that is always the means create as a field, and this field is associated with the cell center. So in open form, any variable you are going to create, it is always the cell center. That is why it is known as the volume scalar quantity. Okay, so when we do the discretization in open form, it is either between the centered or it is we follow are the upwind methods. So upwind method or centered method we followed for the convection terms. Okay, and the diffusive contribution are always centrally discretized. Now the choice, most current choice is generally follow the central discretization term. Okay, and which raises a particular problem with the pressure correction approach. Okay, so this type of the declaration where we declare the every variable at the cell center, we call it as a collocated mesh. Okay, so we can say that the in open form generally we follow the collocated kind of the meshing. So let's take this is the discretizes this is a 1D problem, okay, where this I is the cell center, where we are declaring u and p, well, u as a volume vector field and p as a volume scalar field. Okay. Now, if you want to discretize this continuity equation, so we can write it. So we are following the cell-centered discretization method. So if we want to discretize this del u upon del x equal to the 0, so we can write it as this only. And if you want to discretize this momentum equation, okay, so this we are taking this momentum equation for only 1D direction. So we can discretize it as a this is the transient term, and this is the diffusion, sorry, convection term, and this is the pressure, and this is the this this is stress transfer. Okay. Now the as I said that there is problem is that there is no any specific equation for the pressure. Okay. So for that purpose, what we do, we take means we need to come up with the one equations for the pressure terms. So for that purpose, we take the divergence of the momentum equations. Okay. So if we take the divergence of the momentum equation, so we come up with equations like that. Okay. So in this, let me show you the momentum equation in this form. So if we see this pressure is the like a delta into the P. Okay. But when we take the divergence term, that becomes the Laplacian kind of the equation for the pressure, and this is the tensor equations. Okay, and other equations will become the zero because that will follow the continuity kind of the equations. Okay, so what I mean to say that if we take the divergence of this term, so this equation becomes the zero. This equation becomes the one mathematical identity. If you see into the mathematics books, this is becomes the identity, and this terms become the zero. Okay, and this derivation we are following only for the steady state. So that is why transient term is not written here. So if we take the divergence of the momentum equation, so this equations we will come up with, and this is sometimes known as the Poisson equation for the pressure for a given velocity. Okay. Now what we do, so the discretization form of the equation we have already written here. So we have start with a V star velocity. Okay, and this V star does not satisfy the continuity equation, but we assume that it is satisfying the momentum equation. Okay, so this is kind of equation we come up with if we use assume that V star is the intermediate velocity. Okay, now this V star is following the momentum equation but does not following the continuity equation, so that is why need a correction here. Okay, so suppose we are correcting this, if we are correcting this V star by the V dash and we are correcting Pn by the P dash, then we will get the accurate velocity and accurate the pressure. So suppose this V star, V dash and P dash is the corrected velocity and corrected the pressure. Okay, so the idea is that V star we have taken where it is following the momentum equation. Suppose that we are correcting it by a V dash, and after the correction we are getting the accurate velocity, and similarly after the correcting the pressure we are getting the accurate the pressure. Okay, now if we put into the these two equations, that is the momentum equation and continuity equations, so this, since we are assuming that this is the corrected velocity, so this velocity should follow the velocity momentum equation also, and this Vn plus should also follow the continuity equation also. Okay, now if we subtract this 2 from the 1, so this is the 1 and this is the 2. So if we subtract 2 from 1, and if you use this equation also, Vn plus 1 equal to the V star plus V dash, then we come up with the characteristic. Okay, so that is the V dash equal to the minus delta P upon rho. This is the delta p dash. Okay, so this is known as the velocity pressure characteristic. Okay, how we are getting, we are subtracting equation 2 minus equation 1, and we are using these two equations that we have come up with. So after solving these two equation and using these two identity, we are going to come up with this v dash equal to the minus delta upon rho delta p dash. Okay, so this is known as the velocity characteristic. Okay, so this is so what, again we are taking the divergence of this term, and again we are using these things, and we are come up with the this pressure characteristic. Okay, so from here, if from v star we can calculate the p dash, and from p dash we can calculate the pn plus 1, and when we are using the pn plus 1, then from that I think. Okay, so this is the complete derivation that I've explained on the last two slides. This is the complete derivation. So we are subtracting this minus this one, and we are using these two things, and we are come up with that v dash is equal to the minus delta this del square t into the delta p dash. Okay. Now what we are going to do into the algorithm step. So the things that we have done during the derivation, similarly steps we are going to follow. Set that we will start with the assuming some initial velocity and some boundary condition, and we will solve for the momentum equation. Okay, and the resulting velocity converts the momentum but does not converse the mass. Okay, and from using this we are going to construct the pressure and velocity, and we are going to impose the mass conservation. Okay, so this is the basic general rules that we are going to follow in the simple scheme, and we are going to repeat the process. Now in terms of the mathematical equations, we can write here like this. We will start with the p star. Okay, which is the initial velocity, initial pressure field. Okay, now we are going to solve for the momentum equation to get the u star and v star. Okay, now this u star and v star is going to solve the momentum equation, but does not solve the uh, continuity equation. So using this u star, we are going to find the p dash, that is the pressure character step. Okay, using this pressure character step, we are going to correct our pressure. So this p dash will be added to the p star, and it is going to give you the correct pressure. Okay, now this using the corrected pressure, we are going to calculate the corrected new velocity. Okay, and taking the correct, again this corrected pressure we are going to take as the new gas, and we are going to go to the first step, sorry, second step, and we are going to iterate this until and unless we are going to find the accurate solution. And what in numerical method or in iteration method, what is the accurate means? When the difference between the conjugated velocity and pressure is going to be less than the tolerance value which has been provided by the user, then we are going to say that we have a accurate solution. So that is how this schemes works. And in terms, see, in simple form, this, if we are going to discretize this term, so like if we are going to discretize this momentum equation, then there will be cell-centered value, and there will be some contribution related to the neighboring cells, and this is the body force, and this is the pressure difference. But in simple form, this neighboring cells contribution is generally ignored, and it is ignored just for the simplicity. There is no specific profit for ignoring this, but we just ignored because of the simplicity. Now there is a other solver like simpleFoam kind of algorithm is there in OpenFOAM. I will show you in the OpenFOAM 9 how this simplex algorithm is work, and how simpleFoam algorithm is work. So in simplex we don't ignore this contribution of the neighboring cells, but in simpleFoam we ignore these things. Now in OpenFOAM, this this HU is this UE equation dot H is calculated to find out these values, and this there is one another terms that is known as the like AU equation and U equation dot S. These two terms is important if you're going to code this simple scheme into the OpenFOAM. So what is the AU equation and what is the U equation dot S? U equation A is the generally the means inverse of this uh, AP matrix. Okay, so when we are discretizing this complete matrix, then we have this AP matrix is there, which is the country, which is a matrix which is contributing the coefficient of the matrix for the different values for the different values of the cell center. Okay, and this an un is the contribution related to the neighboring cells. Okay, so this when we take the diagonal inverse of this AP matrix, that is in open form is known as the U equation dot A, and when we take the matrix of this, when we take the inverse of this complete matrix, that is the ANUN equal to the body forces. And if we see the simple algorithm, this terms will be, there will be not any terms related to the neighboring cells, but there should be body forces. So these two terms, if we take, if we calculate in the open form, we calculate the H operator. So these two terms is important in OpenFOAM if you want to code this OpenFOAM solver. So this is the complete step if we see in terms of the governing equation. So this is the discretized form of the continuity equation. Okay. Now this is the important to impose the mass conservation. Okay. And here you can see that this APU means AU A operator, U equation dot A operator, and this HU means U equation dot H operator. Okay. Now we are correcting the velocity here. Okay, and we will update the velocity and we will update the pressure. Then we will go to the step one, then step two, and step three, and step four. Okay, so this is general idea here. Okay, so what is the U equation dot H? Okay, so for that purpose, if you open the zip file, okay, let me show you the file I've shared with you. So I hope you have all you have downloaded this zip file. Okay, so if you open this zip file, so there you are going to find this three folder structure. Okay, so one code I have written just to explain you that what is the H operator and what is the U A operator. Okay, so this code I've just written to made you understand that what is the H operator and what is the U operator. Okay, so if you see this code, this is the velocity field and this is the pressure field we are declaring. I hope you are able to see my code screen. Okay, so first we have declared the velocity field, first, then we have declared the pressure field. Okay, now we have declare one viscosity field, that is the mu. Okay, and we are also defined the phi, which is the flux of the velocity that we have derived here. Now we are creating one FV matrix, okay, where we are including only the divergence term and one related to the Laplacian term. Okay, so this code I have written there. Okay, so that is the divergence term and that is the Laplacian term. Okay, what is the divergence term? So if we see the equations, so if we see this equation, so this is the divergence term and this is the Laplacian term. Okay, so you can see that this is the divergence term and this is the Laplacian term. Okay, now if we see this code, that is the delta dot rho v into v. There is the two times the velocity is there. what is the VM runner? Where from where to get the VM runner? What is the VM runner? Swapnil, what is the VM runner?
Hello.
Yes, yes. Hello.
Sir, actually, in which you have run this OpenFOAM software, like, is there any virtual window or like that?
So in OpenFOAM, there is a method known as a WSL method.
Oh,
So first we
okay,
have to enable the WSL into the your Windows operating system, and
okay.
then you have to install this Ubuntu from MS Store, and then from there you can
Actually, sir, I was not knowing the exact name, so that's why I wrote the VM.
actually I have shared. See, you can also use
We have
the
already shared the details
yes.
in and Swapnil, I think we have already covered that in Nirma session, na? So I think you
Okay,
might know that. Yeah.
okay, sir.
Also, we have shared two document where you can also use the virtual box and we can use the WSL. Okay, so this is the divergence term and this is the Laplacian term. Okay, so that we are means coding here. So now you can see that in divergence term here two this is like a velocity square terms is there. So since we are solving the iterative method, we are not means finding the actual solution. That is why we are creating this phi field. So you can see that this phi field is nothing but the flux of the velocity. This is generally the flux of the velocity. So using this phi field, we are solving the divergence of phi into u. So now you can see that this is a kind of a rho into the v square. So that is how this OpenFOAM treat this divergence term. And this is the Laplacian term with the velocity, viscosity in U. So if you create this matrix, so here two terms is important. Here two method is given here in OpenFOAM. That is the FPM and FBC. Okay. So what is the difference between the FVM and FBC? So FVM is known as the finite volume method and that is sometimes known as the implicit method. And this is known as the explicit method. So what happens when you treat right here FVM, then it is going to create a matrix here. Similarly, when you write here FVM, it is going to create a matrix here. Okay. And it is not going to solve that matrix at this point. Okay, so this is not going to solve the matrix here at this point. But when you write the FBC, so like here you have written phi equal to the FBC into the flux u. So this is not going to give you in terms of the unknown variable. It is going to give here one matrix which has the numerical values. Okay, so this is going to calculate the flux here, and then after calculating the flux it is going to create a matrix which is like a phi matrix. But here it is finite volume method we are using, it is known as the implicit method, and here it is creating the matrix in terms of the unknown. Okay, so that is difference between the finite volume method and finite volume calculation method. Okay, so that is why you can see here that whenever we have a source term, okay, so whenever we have a source term and we have a known terms, then we always use the FBC method. And when we are creating a matrix where we have a unknown terms, okay, in that scenario we always use the finite volume method. Okay. So now we have created this U equation matrix and we have printed this U equation dot H and the U equation dot H. Okay. So just to let you know that how this dot A method and dot H method works. Yes, yes, I will share everything. If you PPT, I will share. Okay. So this just this examples I coded to make you understand that how U equation dot A will work and uequation.h will work. Okay. So I'm not going to compile this. I'm not going to run this. Just you just go and compile by yourself. And I have also included one test case here. You try to run this solver on this test case and just try to figure out that how this A operator and H operator works in the OpenFOAM. So this try to figure out by yourself. And since we have lack of time, so let me just go through the solver uh, as quickly as we can go. So this is the simple form solver. Okay. So this is the two necessary files whenever you are going to compile any solver in OpenFOAM. So this file is always important. That is the fvcfd.h. Okay. So that is like IO stream. So if we have done coding into the C++, you know that what is the IO stream. So similarly to the C++, this IO stream is important. Similar to that, FBC, for OpenFOAM, this fvcfd.h is important. So whenever you are going to do coding, any kind of coding, so fvcfd contains all the necessary file that is required to make any solver into the OpenFOAM. And this is the simple control.h because we are going to use this loop. That loop that we are going to use is related to the simple solver. So that is why the simple control.h is important. Now what we are going to do, we are these are the steps that is required if you want to make any solver. First, whenever you compile any solver, first we are going to check the folder structure. Okay. So what I mean to folder structure. So whenever you are going to compile any solver, first you are going to check that whether it has the zero folder, constant folder, or system folder is available or not. Because until and unless these three folders is not available here, there is no meaning of running any solver. Because solver requires meshing, solver requires the discretization method, solver requires the initial boundary condition, solver requires the meshing. So this all the information is given in these three folders: zero folder, constant folder, and system folder. Zero folder contains the initial condition, constant folder contains the fluid properties and the meshing, system folder contains the time control as well as the discretization method. So that is why first task is to check the folder structure. Okay. Then we are going to create the time object. This OpenFOAM works on the object or OpenFOAM also known as the object oriented programming. Okay. So whatever the things we are creating in OpenFOAM, you are generally creating an object. Okay. So if you talk about the time, we create a object of the time. If we talk about the machine, we create generally the object of the machine. So anything so you are seeing OpenFOAM, that is known as the either a object you have created or any method related to that object. So because OpenFOAM works under the object-oriented programming. Okay, so we created the tie object, we created the meshing object. Okay, now we are creating the object for the looping. Okay, and here we are using the simple loop. So we will have a simple method. Otherwise, there are other methods also, that is the piso and pimple. Okay, so this four object we have created. Okay, one is related to the folder, time, and mesh and object. Okay, now after that we are going to code the simple algorithm. So for that simple scheme, we have some assumptions. Like simple scheme solve for the steady state problem. We are also taking solving simple form for the incompressible flow. Okay, so incompressible means density is constant. We are also assuming the kinematic viscosity, and we are assuming it as a Newtonian flow. And this simple form algorithm works for the role inertia because of some assumptions is assumed here, and we neglect the body forces. Okay. Now here in simple algorithm, there is one trick that because we are assuming the density constant, density is not changing. So that is why simple scheme solve for the p by rho. Okay, so if you see the test case in the simple form, and if you see the test case in the other solvers like Biont Pimple from other solvers, you are going to see that the unit of the SI unit of the pressure is different in those two folders, because in simple form we solve for the P by rho, but in other solvers we solve for the pressure field only. So that is why this is the difference here, because here we assume the constant constant density, and also there is no transient term. So that is why this assumptions we can take that we can solve for the p by rho. Now these are the schemes. These are the steps that we are going to follow. So we will start solving with the u, assuming the previous pressure. Okay, now we will calculate the A minus H, and that is the H, that A operator we are going to take and H operator we are going to take. Then we will go for the pressure characteristic, and then we will update the U and we will update the pressure. Okay. Now this four step that we have taken, check the folder structure, check creating the time object, creating the mesh object, and creating the looping object, that we are going to perform here. So this is the first step. We have where we have checked the folder structure. So this set root case dot h is the for checking the folder structure. Here we are creating the time object. Here we are creating the mesh object, and here we are creating the loop object. Okay. So if you want to know that what is the code written here, so you can always go to the OpenFOAM document. You can always go to the, and you can see the coding here. Okay, so all things about the OpenFOAM create time h has been written here. What is the create time h, and how it is the different library is attached with the create time h, that you can see here. So this is the simple code of the create time.h, and if you are calling this create time.h header file, means you are calling this complete code here. Okay, so this create time.h means we are calling this complete code here. Okay. Similarly, there is some coding related to the set root case.h. Similarly, there is some code is written here for the create mesh.h. Similarly, create control.h. And this file we are including is from a separate file. So if you see here, so this is the create fields.h. So that we are creating from our side. Okay. So this create fields.h that we are defining from our side, where we are going to create the different variables. Okay. For example, in our case, this pressure field is required. So that is why we are creating one volume scalar field, which is the pressure field. And then again, we are creating the volume vector field, which is the velocity field. We are creating the surface scalar phi field. As I told you that this phi is important because we are iterating, we are trying to make this non-linear term, which is the divergence term, sorry, which is the convection term, and we are trying to take this phi and u as a separate variable, and using this separate variable, we are trying to make this term as a linear term. Okay, so we are trying to remove the non-linearity using this treatment. So we are declaring phi, and we are interpolating this u onto the surface, so onto the cell surface. So this is going to calculate the surface vector. So we are trying to mistaking the product between the u and this surface vector, and we are computing it as a surface scalar field. Okay, and then by using this phi and u, which is the current time velocity, we are calculating the product of this phi and du, and this way we are trying to avoid this non-linearity of this term. Okay, and this p word we sometimes take to calculate the relaxation factor. So if in simple in steady state, this relaxation is important. So this we are storing the present time pressure into the p word. So this is way of the storing the pressure current time field into the present time field. So we are storing this p word to apply the relaxation factor. and we are creating one dictionary, that is the transport properties, where we are going to define this viscosity. Okay, so first we have created this dictionary, and in this dictionary we are creating this variable, that is the viscosity. See, that is why I told that OpenFOAM works on the object. Without declaring any object, you cannot define anything. See, even if you want to define this viscosity, we have to declare one object. So that is why we declared one dictionary, which is a kind of object, and using that object, we are defining one variable, that is the viscosity. Okay. This is similarly, we have created one dictionary, that is the FP solution. And in FP solution, again, we have defined one object, which is a type of the IO dictionary. And using this object, we are creating some variables, that is the alpha, pref cell, pref value. Okay. Okay, so this is something to provide the relaxation factor. Okay, this alpha is used to provide the relaxation factor. Now, once we have created our time and control loop, so we can start with our looping. So here we have started our simple loop. Okay, here we are going to print the current time step value. Okay, see this one thing you can see that if you see this create time dot h. So if you see this create time dot h, so here we are creating one object runtime. Okay, so we have taken the type of this runtime is the time, and we have created one object of the runtime. Okay, now whenever we want to call any method of time, you have to call this runtime. Okay, what I mean to say that this is the object with the name of the runtime has been created. Now, whenever you want to call this runtime, any method related to runtime, we have to call this object only. So this runtime dot time name means this is the object, and we are calling one method of the runtime. Okay. See, this is a means if you are not able to follow the coding and everything, because this is advanced programming thing that I'm explaining here. So maybe if you buy that advanced programming course, or if you will able to part of this CFD course, we are going to explain everything from the basics, and definitely you are going to catch everything whatever I am explaining here. What is the object? What is this method? And why this runtime? How this runtime has been created? What is this time name is here? We have explained everything. Every object of the time object has been explained in our programming session. Okay. Now, if we want to write this Navier-Stokes equation, so Navier-Stokes equation should have the convection term, diffusion term, and this pressure gradient term. So this we can write in terms of the this matrix. Okay. I have already explained that what is the finite value method and what is the finite value calculation method. Okay. So this is the convection term, this is the diffusion term, and this is the pressure gradient. As I told you that we are ignoring the body forces, so that is why there is no any body forces, and also we are ignoring the transient term because simpleFOAM is a simply steady state solver. Okay, so this is the coding for the momentum equation, that is the convection term, diffusion term, and the pressure gradient term. Okay, and again see that I always told you that source term is always treated as the FBC method. So this is the pressure is the source, pressure is acting as a source term. So that is why it is taken as the uh, FBC method. Whereas whenever you have some unknown, we always treat as a FVM method. We always take as an implicit method. Okay. Now once we have created this method, okay, so it is going to, so this is going to give you like 1 AU equal to the minus P. So this kind of the matrix it is going to generate. So A will be some kind of matrix, and there will be one unknown matrix, that is the AU, and that is the minus P is the some value. There will be some numerical values. Okay. Now when you apply this U equation dot solve, it is going to solve for the velocity here. So it is going to solve for the u values. Okay. So this u equation dot solve means we have some initial value, some u star, that you can say that is the u star, kind of a u star. Okay. Now we have calculated this u equation dot a and u equation dot h, that you will already know that what is the u equation dot a. We have already know from here. So this AP, that is the contribution of the cell-centered velocity, coefficient of the cell-centered velocity is the AU. And if you considering the body forces and the neighboring sources, then this is the EHU, that is equation dot H. Okay, so that we have calculate here. Okay, now we are taking the inverse of this A matrix. Okay, so that is A inverse equal to the 1 by A. Okay, since A is the diagonal matrix, so it is very easy to take the inverse of the diagonal matrix, that is the 1 by A. This kind of the rule is applied here. Okay, so if you have a non-diagonal values, then you cannot apply this rule. But if you have only diagonal values, then you can calculate the inverse matrix just by dividing that matrix by 1 by A. Okay, now after calculating this, we have calculated this h by a, that is the A inverse into the h value. Okay, so this h by a we have calculated here, and after this we have calculated the surface scalar matrix of this A inverse. Okay, now here we are solving the pressure characteristic. Okay, so this is the kind of the Laplacian of the A inverse into the P equal to the divergence of h by A. So this step we are solving here. Okay, and this is also going to give you a matrix like a P, some matrix into the P equal to the some value, some numerical value. So this is not being solved here, but when we apply here P equation of solve, this is going to solve for the pressure. Okay, what we are solving here, we are solving this equation. Okay, so if you want to compare this equation with this, okay, so you can compare like that. So this is kind of a, see, here you can ignore the row because I already told you that in simple form we solve for the P by rho. So we can ignore here the row. So we have just A inverse into the delta P equal to the AUP into inverse into the HU. Okay, so this equation we are solving here. So you can compare here that A inverse into the P equal to the H by A. What is the H by A? H by A is nothing but A inverse into the H. Okay, so see here that H into the A inverse U, and here we are solving A inverse into the delta P. So this equation we are solving here, that you can correlate here. This is the equation that we are exactly solving here. So here we have a corrected the pressure. Okay, now using the corrected pressure, we can correct the velocity here. Okay, now we have the corrected pressure here. This lines gives the corrected pressure, and using this corrected pressure, we can calculate the corrected velocity. Okay, and again we calculate the phi field, because phi field again is going to be put here, because here we are trying to avoid the non-linearity. So that is why we are trying to multiply phi and u. Okay, and sometimes to make the steady state solver faster, we use the relaxation factor, because the idea is that in in iterative method, the difference between the consecutive pressure field and consecutive velocity field should be smaller. So what idea for the relaxation factor is that we can take the some contribution of the last time step value. Okay, so here you can see that this is the present velocity and this is the old velocity. Sorry, this is the present pressure field and this is the old pressure field. So based on the user alpha value, whatever the user alpha value should be provided, it generally it should be between the 0 to 1. and based on the value provided by the user, either it is the 0.3 or 0.4, whatever the user provided. So based on that alpha value, it is going to take the contribution of the present pressure field and the uh, last time step pressure field. Okay, so the idea of the relaxation factor is to arrive at the steady state solution very fast. Okay, so if your solver sometimes not giving you correct accurate value at after a suppose 1,000 iteration, then sometimes this relaxation factor is helpful to arrive to the steady state solution very faster. So this is idea about the relaxation factor. Okay, so means sometimes it is important and sometimes this is not important. Okay, so I think you have no idea that how this is started. So first we have, find the u value using the initial guess of the pressure field. Then we have corrected the pressure field. Okay. Now using the corrected pressure field, if you required, you can take the some contribution of the last time step pressure value, and using that corrected pressure value, we correct the velocity. Okay, we calculated the phi field, and again we will go to the uh, start of the iteration. So this will loop until and unless we will get the final solution, final accuracy. Okay, so this is the complete algorithm. If you want, we can compile here. So I can go to the my simple form. Okay, so this is the simple form solver. So by changing the directory cd simple form, I have come up into the my simple form solver. Now if I type OF90, so this is required to create the OpenFOAM environment. Okay, so OpenFOAM environment has been created. Now first I can type wclean.l. So it is wclean.all is used that if already some solver is present with the name of the my simple one, then it will clean the software, clean the means where the solver, where the application is built up. Okay, so this wclean all is required there. If you want to some compile some solver, you can use the wmake method. So it is going to run it, and if there will be no any error, it is going to give you the solver. Okay, so this is just a simple form, and if you want to compare with the other algorithm, so like this is the simple scheme that I told you. Okay, so we start with the u equation, and we will solve for the u equation equal to dot delta p. Okay, now this is the where we have corrected the pressure 1 by a into the delta p equal to the this equation we have corrected for the pressure. Okay, sometimes we have a message who is which is not orthogonally correct. Sometimes in that scenario we provide the some non-orthogonal character. Okay, so these things we have already explained into the advanced classes, advanced open home classes. And after correcting the pressure, we will have a corrected velocity, and this will loop until and unless we have a some accurate value of the pressure and velocity. Okay, and if you want, you can provide the under relaxation for the u, and sometimes the under relaxation of the velocity also. Okay, so idea of the relaxation is the simple that you want to take some contribution from the small type step time step. So similar to pressure, we can also do for the temperature if you have temperature as a field variable, and if you have a velocity as a field variable, these things you can also do for the velocity also. Okay, so based on your requirement, you can take the relaxation whether you want or not. So this is the idea about the simple scheme. Now there is slightly difference between the piezo scheme. Okay, and you can see that in earlier solver we have just iteration, this iteration is there, and there is if there is a non-orthogonal character, this iteration is there. Okay, but in piso form, first of all, the piso form is the uh, transient solver. Okay, so if you see that in piso form there is a ddtu term is there, so this is the time transient solver also. Okay, So that is why you can have a this time loop also will be there. And sometimes what happens that we provide the n characters to the this solver. So the idea is that anyone have any question? So what happens? The idea, the simple things is that we want to find the accurate velocity and pressure. Okay. So instead of going to the first step, sometimes we just try to correct from this step only. Okay, where pressure step. Okay. So instead of going to the first step, that is the U equation equal to the minus delta P, we provide n characters that we just go to the this pressure character step and try, suppose you provided n characters equal to the 1 or 2. So it will correct this step two times. Okay, then go to the end step, then it will go to the final step. Okay, so this n characters is the different from the simple scheme, and that is only difference between the piso scheme. Okay, that instead of going to the first step, that is the E equation equal to the minus delta P, here we go to the pressure character step multiple times, and then after going to the multiple times, then we go to the start time step. Okay, so that is the piso scheme, and the combination of the simple and piso scheme is known as the pimple scheme. Okay, so this is the basic of the simple scheme and the piso scheme. And if you have any question, you can ask me. And if you have not understand, means I think I have explained from the basics, so I think we have idea that how this solver is working here. Uh, Still, if you have any question, you can ask right now. Otherwise, please join our sessions, and you will get the multiple chance to interact with us, and you can ask any type of questions related to the session or related to the your project or related to the open form or related to the machine learning. Okay, so this is all about from today's session. It's already 4:30. We have planned this session up to the 4 p.m. So we'll already we are ahead of the 30 minutes. You have any questions? And I would suggest that I have shared this zip file. So try to open this zip file and first compile this solver and run this solver and this test case. And after that, I have also given this my simple form solver. You also compile this. And here, similar to this, I have just commented out everything. The zip file you are going to get, I have commented out everything. From your side, just try to remove the comment and make it as a code and try to compile from your side. And this is the test case again I am provided. And using this solver, I have get this final result. Okay, so the solver using that developed solver, I have get this final result. So you also try to find this kind of result using the paraform, and then this session will be useful for you because this is a hands-on session. So just don't watch this session. Try to practice from your side also. Okay. So if you have not any questions, then I think we can end this session here. I will share the registration details and everything into the group very soon. And whatever the content we have covered here, I'm going to provide you the slides of those contents into the group. Okay. So thank you to all of you for joining this session.